Good morning, everyone. I want to start again. I've already introduced this class before. But I want to kind of start with a basic introduction. Then in the subsequent classes, we are going to be looking at some of the concepts in depth. Okay, so the contents, this is going to be a kind of a general overview of what we are going to be looking at when we discuss expert system. So first we start with introduction to expert system, give a little historical background, talk about the components, the architecture of an expert system. Then in looking at the components, inside of the components, we have the knowledge representation, inference mechanisms, and then we talk about expert system examples and different application areas where areas where we can apply expert system. And then we talk about the challenges and the benefits. I want to believe we'll be able to do all this in this particular lecture. Okay. So the first question we're going to ask ourselves is, what is an expert system? What is an expert system? We said that it's a computer program that uses artificial intelligence to mimic the decision-making abilities of a human expert. In other words, generally, we want to replicate the behaviors of a human expert in a machine. Okay, and there are several reasons why that may need to be done. So as we go further, we'll see why it may need to be done and why it is necessary that these things are done. Okay, so expert systems are widely used, especially in places where the domain experts are limited. For example, in the area of medicine, finance, engineering, and several others. So when we talk about medicine, we're not just talking about human medicine, we're also talking about veterinary medicine, so on and so forth. So we want to look at the brief history of expert system. So this expert system began around the 1960s. That's when we can say that it is the beginning years of the expert system. And it starts with Dendra that was developed at Stanford University, which was used to infer molecular structure from mass spectrometry. Okay. So next in the development is the mycin, which also came from the Stanford University, and it was actually designed for bacterial diagnosis, for bacterial infection diagnosis and treatment recommendation. So this particular expert system, the mycin, which was developed in 1972, used a rule-based system, rule-based approach to provide medical advice. And it was one of the first systems that demonstrated the potential of an expert system in a complex decision-making task. Okay, furthermore, in the 80s, we have the growth and commercialization when expert system began to be commercialized. So when people began to sell expert system. So at that point, we have the Prolog and the LIPS. Prolog was developed in the 1972 as the language, and LIPS also a language which became very popular. Those are languages that became very popular for the development of expert system. And this was basically because of their support for symbolic reasoning and pattern matching. Okay, so in that 1980, around 1980, the XCOM was developed by Digital Equipment Corporation to configure orders for new computer system. that system they developed demonstrated significant cost savings and efficiency improvements that led to increased interest and investment in the domain of expert systems. Then, still in that 1980, there was this commercialization such that many companies started implementing expert system in different domains. So this is a little thing that we can talk about the brief history of the expert system. Okay, now when we talk about expert system, what do we see? I want to believe that you are seeing this picture very clearly. Okay, so we now want to talk about the components, the core components of an expert system. Okay, so the very first component, when we talk about experts, we are talking about the domain person or the domain professional, a professional in a particular domain. So the component of an expert system largely includes that particular domain professional. Okay, so that's the very first person you can see in the expert system space. You see the human expert here, and that is the very first person you will see, the very first component that is very, very necessary in an expert system, because it is the knowledge of that human expert that will proceed further into coding it into the machine, such that the machine will begin to behave like that human expert. Okay, so next we have the domain engineer, which is basically where you belong to, or what we call the knowledge engineer. The knowledge engineer is the person that elicits the knowledge of the domain experts. There are several ways that knowledge is elicited from an expert. There are several ways that you can use to elicit knowledge from the domain expert. Okay, so first is we have the domain expert himself. Second is that we have a non-domain expert, or what I may call an AI engineer, that is saddled with the responsibility of getting the knowledge that the domain expert has. Okay, and this knowledge is actually what we want to computerize. So when the knowledge engineer gets the knowledge, there are different ways. There are different ways you can use, or rather, we have the expert system core component. Okay, and in that core component, we'll have the knowledge base, which we may tag as something like database. But what it stores is actually the knowledge of the domain experts. And there are several ways of knowledge representation, how knowledge can be represented. We are going to come to that. Then we are going to have the knowledge base. This is the expert system itself. Okay, but this is the domain expert. This is the knowledge engineer who uses the knowledge of the domain experts to develop an expert system. So inside of the expert system, you have the knowledge base, you have the inference engine, and then you have the user interface. Then another personality you see here is the user, who may actually not be an expert. And like I said, the essence of an expert system is actually to replicate the knowledge of the domain experts, especially in the areas, or rather in places where the experts, or rather experts, are lacking. For instance, we can develop expert system for medical diagnosis for use in remote villages where there are no doctors. Okay, and for instance, I don't know the number of medical doctors we have in Nigeria, and I don't know the number of veterinary doctors we have in Nigeria. And I can bet you that there are several persons in the domain of agriculture that have not, and they are not intending to actually consult a veterinary doctor with respect to their animals. Okay, and also there are several of them that will not consult animal scientists, or rather take their plants to plant clinic, okay? So you discover that there is a huge need to develop expert systems in that regard, in these several areas that I've mentioned, okay? So next we are going to look at the development process of an expert system. And if you're able to understand the first one that I just mentioned, or rather the previous slide this previous slide, if you're able to understand this, it is easier to pick up with this. So first of all, the expert system development process is saddled with the operation of first of all defining the problem you want to solve. So first of all, there is what is called problem definition. Okay. Now, before I continue, I hope you can see my screen clearly.
Yes, sir.
Okay. So there is the problem definition. You want to define a problem you want to solve. Okay. When you define the problem you want to solve, you know, the understanding, please, I want you to pay serious attention in this place, because there's a tendency that you are going to see it in your examination. Okay, first of all, there is the very first process of defining the problem you want to solve. So the understanding of that problem will inform the data that you are going to collect. I hope I am making sense. Okay? You need to first define the problem. What problem am I going to solve? What problem am I looking at solving?
This amount.
Does anybody want to say something? Please, if you want to say something, please raise your hand, and then I will recognize you and you say something. Thank you. So there is, first of all, the definition of the problem you want to solve. There has to be a proper understanding, because it is when you have understood the problem you want to solve that you will be able to go ahead and then coin out questions that will answer the problem. Okay? Now, you have a problem, and that problem is going to be placed in form of questions. Okay? And when you are able to have an answer to your question, it becomes the solution to the problem that made you to ask such questions. Okay, so first, definition of the problem, you have to write it down. This is the problem we want to solve. Now, before I proceed further, when we talk about expert system, there is a direct question we are asking. There is a direct need in our heart. There is a direct understanding we want to grab concerning a concept, concerning a particular knowledge domain. Okay, so when we are talking about an expert or an expert system, we are talking about a direct, something that is peculiar to a specific domain. So if you are talking about a medical expert system, you are talking about medical expert system. And if you come to medical expert system, it's going to depend on the area of medicine that you are seeking a solution from. Okay. Okay. Now, when you have defined the problem, the next thing is, how do I represent, how do I gather this knowledge? How do I gather this knowledge? How do I elicit this knowledge? So there are different techniques of eliciting knowledge from the domain expert, which you are going to see in the course of the study. Now, when you have elicited knowledge from the domain experts, either through interview, questionnaires, and so on and so forth, when you have elicited knowledge, then the next thing now is, how do I represent this knowledge so that I can or I will be able to access it from the expert systems inference engine? Yeah, we are going to come to that. Okay, so how do I represent this knowledge? And there are different ways, about 3 methods of knowledge representation. Okay, you have collected the information, you have acquired the knowledge from the domain experts. How do I represent it? So if we are going to look at, or rather, if we want to talk about the basic web development process, you discover that there are 5 systems, there are 5 system database. Okay, and there are table databases, like if you are using the MongoDB, it's not a tabular structure database. And then if you are using MySQL, you are talking about relational database management system, okay, that has to do with tables and schemas. Okay, so there are different ways you can as well represent knowledge in an expert system. Then after representing the knowledge of an expert in a particular way, the next thing is the system design. You design the system in such a way that you can assess the knowledge and present it. Now, inside of the system design, there are 3 things that you can see, as you can see here. Okay, there are 3 things that you can design in your system. Number 1 is the user interface, UI. Number 2 is the inference engine. And number 3 is the knowledge base. So these are the 3 things that you are going to actually design, okay? 3 things that you are going to design. Just like you are designing in your web development, okay? There is user interface, there is inference engine, and there is knowledge base. Okay, in your web design, you can call this one your database. In your inference engine, you can call it maybe your API, or you call it, what do I call it now? Your backend. Okay, and then you have your user interface as usual. Okay, now after developing this and doing the necessary linking, you will notice that this thing is in a box. These 3 things, they are in a box. Okay. So that box is actually the system you are testing. Now, the next thing is to test the system to see if it is actually working well. Now, how do we know that an expert system is working well? We are going to test it, or rather compare the output. We are going to compare the output of that expert system with the knowledge of the domain experts. Okay. That is an evaluation process, okay? So if you develop an expert system, how do we know whether that expert system is working? We bring that expert system, maybe we ask some basic questions and see the information, or rather the answer that the expert system is going to give us back, okay? And then we now go to a domain expert and say, please, you ask the domain expert the same question. And then you can use your yardstick to check what is the similarity index between the 2. Are they very close or are they far apart? Okay, that is it working well? This is the evaluation process. And if we are satisfied that the expert system is actually working as we expected, the next thing is to deploy the expert system. Okay, now when we deploy the expert system, as we are using the expert system, there is need, because education, or rather knowledge, is dynamic, there is need for maintenance of the, or rather maintenance and the update of the expert system, because new knowledge is going to spring up in different domain of study or different domain of learning. So this is the basic expert system development process. Are we together? Okay. Now, we are going to now start looking at different areas. Now, before I go further, I just noticed that when you look at this now, when you look at this slide, there's a slide that is missing here, and that is the slide that is supposed to talk about knowledge acquisition. Now, how do we grab information before I go to the next? How do we grab information about the knowledge of an expert system? Okay, how do we grab information? So there are different ways that we can use to collect data concerning an expert system. Number 1 is by interviewing the domain experts. Maybe you want to develop an application that teaches people how to farm, okay, how to farm a particular crop. Okay, so what are you going to do? You are going to meet an agriculturist that is specialized in that area, and then begin to ask the person, what is the process of doing this and that, this and that? And then we'll start with telling you how to clear your ground, how to prepare the soil, how to water the temperature that the soil is going to, be to maintain some certain thing, the pH level of the, all of those information is you are acquiring knowledge, okay? Acquiring knowledge. And this is actually done. This one now, I'm talking about interviewing a domain expert. Then that's number one. Number two is that you may use questionnaire to compare, okay? You still ask some questions to different domain experts and see what their responses will be to that answers that, to the questions that you pose in the questionnaire. So when you collect those answers, you aggregate them together and it forms a knowledge corpus, okay? A piece of kind of a knowledge base for the expert system you want to develop. Another way that you can use to represent, another way you can use to acquire knowledge, I've talked about interviewing, I've talked about use of questionnaires. Another thing is to maybe access different corpuses. And when I talk about corpus, I'll talk about load of text. For instance, a textbook that defines the particular domain of application that you want to, or particular knowledge domain that you want to elicit, okay, to use in your expert system. Okay, so you can begin to gather books, materials, handouts, lecture notes, and so on and so forth that are tailored towards that particular expert system that you want to develop. So you begin to elicit knowledge from those sources and so on and so forth. So you are going to be going to get some of these things that I did not mention, knowledge acquisition processes or knowledge acquisition methods. Some may come in the area of observation, because when you are actually interviewing an expert, there are some certain things that he may be saying or he may really not say, but you observe him do. For instance, if you enter a poultry farm and you are asking questions to the farmer, you know that there are some certain activities that he may not be able to communicate. There is a knowledge that a farmer has, but is not able to communicate it. So you as a knowledge engineer to have the ability to be able to elicit knowledge from that angle. So actually, that's part of the challenges of an expert system, the ability of the expert to even communicate the whole knowledge or the whole thing he knows about the domain where he's working. You can bet with me that there are several persons that know a lot, but are not able to communicate a lot. Okay, so that's one of the limitations we have when developing expert systems. Okay. Okay, now let me go further to knowledge representation. So how do we represent knowledge in the expert system? We say that knowledge representation defines the different ways an expert's knowledge can be represented for easy and efficient storage and retrieval. Okay, now it's not as if we cannot dump the whole corpus in a database, no, but we are looking at the way that we can use to represent this knowledge for easy and efficient storage and retrieval. For easy and efficient storage and retrieval, okay? So we should be able to design our knowledge base in such a way that we'll be able to add information to it easily and to be able to receive information from it, okay, easily. There are basically three methods that are used or that are involved in knowledge representation. One of them is the rule-based method, rule-based, frames, and then we'll talk about semantic network. Maybe I'm going to skim through these things in this class, and in our next class, I want to believe that I'm still going to come to it again in one way or the other. So as we proceed, we may see ourselves talking or touching what we have done before. Because as I said from the beginning of this lecture, this is going to be a kind of an overall lecture that I'm going to be giving in this particular session of expert system. So it is possible that you revise this particular lecture. It's a very important lecture that encompasses every other aspect that I will be taking you on, with the exception of one other topic that I'm going to talk about. Everything that I'm going to be teaching in expert system is basically compressed in this particular summary. So I want you to take this particular lecture very seriously. Okay, we talk about rule-based representation. So this approach uses conditional statements, which you already know, that often comes in the form of if-then rules. It uses it to represent knowledge of human experts, okay, in a structured and logical format. So these rules are the foundation upon which the inference engine operates to derive conclusion or make decisions. Now, the word inference is to draw conclusion. What do we conclude about this? Okay, if this is this, then we conclude that it is this. Are you getting what I'm saying? So let's look at the if-then rule. Number one is that we have a structure. A rule is typically written as if conditions, then action. Okay, so we have two parts. Number one is the if. The moment we mention if, then we look at the conditions that are going to follow. So if the temperature is high and the person is experiencing nausea, then he may have malaria. Are you getting what I'm saying? Okay, if somebody's temperature is very high and is feeling nausea, then we just say then he has malaria. Okay, so for example, it says if the patient has a fever and a sore throat, then what is the diagnosis? Diagnosed as possible strep throat, and the person is having a strep throat. Okay, then another thing that we have there is antecedent and consequence. So in the area of antecedents, we have the if part, the condition or premises that need to be satisfied. Okay, and if it is satisfied, we now have the consequence, which is the then part. Okay, the consequence is the action or conclusions that follow if the antecedent conditions are met. So this is the basic thing that we talk about when we are talking about the rule-based representation. Okay. Now, we talk about frame representation. Frame representation. Frame representation is a knowledge representation technique in artificial intelligence that uses a structure called a frame to represent stereotype situation. So in each frame, it will contain slots, which we can tag as attributes and properties and their associated values or procedures, which is called methods. Okay, now, inside of this frame, we'll have the slots. Let's look at the slots. The slots represent attributes or properties of the frame. Now, inside of the slot, we'll have the slot value, the default value, and the facets. The slot value is the actual data or reference that is stored in a slot. The actual value, we're going to be looking at this in example. Okay, now default value is a predefined value that can be used if no specific value is provided, while the facets represent the additional information about the slots, such as the constraints or procedural attachments. Okay, now the components of a slot. First, we'll have the slot name, which identifies the frame. Then we'll have the slots, which represent attributes or properties of the frame. Now, inside of that slot, we now have all these things that we have mentioned. Okay. Is coming. Okay. All right. Okay, now let's look at frame representation example. Now, by this example, you will understand. Example of a frame, we say, imagine a car frame representing a car. Now, the frame name is going to be the car. The name of that frame is going to be the car. Now, the slots is going to have some certain things inside that define the properties of that car. Now, under the slot, we have what is the make of that car. The car can be Toyota, it can be Honda, it can be Ford. And then what is the model? If it is Toyota, is it Toyota Corolla or is it Toyota Camry and so on and so forth? Then what is the year? Because inside of our system, maybe we are developing an expert system that will help us to diagnose the fault in a car. Are we together? Maybe we want to develop an expert system that will help to diagnose a fault in a car. So first we ask the expert system will ask you, what car are you bringing? And you say, sorry, what vehicle are you bringing? You say it's a car. It's okay, what's the make of that car? You say it's a Honda car. Okay, he says, okay, Honda car, what's the model and the year? He says it's Toyota Corolla 2020 model, or it is Toyota Corolla 2020, and so on and so forth. So the moment you are doing that, you are going deeper into that particular thing. Okay, you can go further to ask you what's the engine type, and what's the horsepower, and so on and so forth, depending on what you want to use the expert system to do. So you see a way to actually develop a frame representation of an expert system, or rather for an expert system. Okay, then we have the semantic network. We'll have the semantic network. Okay, a semantic network is a knowledge representation technique that is used in AI, which models the relationship between a concept in a network-like structure. Okay, models the relationship between a concept in a network-like structure. These networks are composed of nodes representing concepts or objects and edges that represents the relationship between the different concepts we are talking about. Now, if you look at this example, I don't know if you can see it clearly. Okay, I don't know if you can see it clearly. Can you see it clearly?
Yes, sir.
Okay. You can see Ale is a, so this is a, actually defines the relationship between Ali and the employee. So you say Ali is an employee, and employees are actually human beings. So an employee is a human. So then you come to the place where you see John. John is actually a human being, but the relationship between John and Ali is that John is a supervisor to Ali. Okay, so Ali will be John's supervisee. We can say that John is married to Sally, and Sally is a human, and John is a supervisor. Okay, and since John is a supervisor that can do something, John is actually a human being. So we see how we can actually relate concepts with other concepts using semantic networks. Okay, now you can as well use this thing in a has manner. Okay, you can say this guy has fever, and fever is this and that. So this is a way that one can as well represent knowledge in a network manner. Okay, so that is semantic network representation. So like I said, in the next class, I'm going to go deep into this rule-based representation, frame representation, semantic network representation. I'm going to go deeper into each and every one of them. It's going to appear as if we are going to be repeating this class, but whatever you are not able to grab in this particular class is going to actually be made clearer in the next class that we're going to be having. Okay, we have the inference engine. Now, what it means is that if we go back to this particular stuff, we have talked about knowledge acquisition, and then we have talked about knowledge representation, right? So the next thing that we're going to be looking at is the system design. And inside of the system design, we have this. And inside of this, the very first thing we are looking at is IE, which is the inference engine, all right? So let's go further to it. So what then is inference engine? Inference engine. So there are two things that we want to look at here. The inference engine itself versus the inference mechanism, okay? So why the inference engine is the seat of expert system decision, the inference mechanism defines the method and expert system engages. The method that the expert system engages in, okay, in arriving at some certain decision that it makes. How does an expert system make decision? How does it arrive at the conclusion of the decision that it wants to make? So you see now we are looking at the EIA itself, the inference engine itself, how it works behind the scene. Inside of that inference engine, how does it work? So there are two most important, or rather the two most important approach that an inference engine uses to arrive at a conclusion that it wants to make. Number one is what is called a forward chaining method, okay? And this inference mechanism uses data-driven approach. It uses data-driven approach to arrive at a conclusion. In other words, there are facts that it has to have in its hands for it to be able to make decision, okay? So it's not making arbitrary decisions. So when the expert system is asking you questions, it's actually eliciting facts from you, and it is that fact that is going to compare with what it has already in the knowledge base in order to arrive at a certain conclusion. Okay, then we have the backward chaining. So this one starts from okay, I'm going to look at the forward chaining itself. I'm just explaining the concepts or the methods. Okay, now we have the backward chaining, and this backward chaining is driven by the goal it wants to get at. For instance, you say that somebody has malaria. Now, there is a conclusion that he has malaria, but how will the system actually agree with you that he has malaria? So it starts from the malaria goal, because you have actually concluded that this guy has malaria. Now it starts from that particular area to drive back to see if indeed this guy has malaria. But if he does not have malaria, then he will come back to say, no, he does not have malaria. Okay. So that is backward chaining. While the forward chaining approach is data-driven, the backward chain approach is goal-driven. Please take note of these two important concepts. I said the forward chaining approach is data-driven. It's based on the data that it elicits from the user to dig into the knowledge base in order to be able to say this is what is happening or this is what has happened. But the backward chaining approach uses the goal, what has happened already, to drive back at the symptoms, or in order to verify whether it is actually what has happened. Okay. Now let's look at the forward chaining in itself. Okay. So I want to believe that you are seeing the diagram at the right. Okay. So the forward chaining method makes use of available data and uses it to infer conclusions or reach decisions based on the logic applied to such data elements. Okay. Okay. Then the forward chaining process will start up with initial facts. There are facts, yes, there are facts. Okay, we'll start up with the initial facts and then find rules where conditions are satisfied between known facts. So during this execution process, the system applies the rule and then adds new facts to the working memory. Okay, this process is repeated until no more rules can be applied or a goal is reached. Let's look, for instance, an example. Let me just take an example that you usually see around in chemistry when you are doing your qualitative analysis in chemistry. For instance, you want to check whether a gas is what you suspect that it is. Okay, so for instance, you are heating a compound. You are heating a compound and a gas is evolved. The very first question you may need to check, or rather the very first observation you may need to note, is the color of the gas. Okay, so it's possible that when you are heating the gas, you are heating the compound, the gas that is being emitted is actually colorless. Okay, but it is colorless, but you are perceiving some sound around it. Sorry, some odor around it. Okay, so you say that is a colorless or odorless gas. Okay, so first is colorless. You establish that it is colorless. Then the next question may be, is it odorless also? So you say colorless and odorless. Now you can proceed to a decision. If it is colorless and odorless, then we suspect maybe we suspect nitrogen, we suspect oxygen, we suspect carbon dioxide, and so on and so forth. All these are gases that do not have colors, okay? And for instance, you don't perceive the smell of oxygen or the smell of carbon dioxide and so on and so forth, rather the smell of nitrogen, unless you talk about nitrogen compound like ammonia and maybe ammonium and so on and so forth, okay? So, but apart from that, you have a colorless, odorless gas that is evolved. Now, the next question is that we want to arrive at a certain decision. We'll now check maybe inference checking, or I can't remember exactly what it's called in chemistry, okay? You can now say, let's use inference test, for instance, to check what final gas is this. So we can say, usually in chemistry, you say pass it through lime water, and let's see the reaction of that particular gas with lime water. Now we discover that when a colorless, odorless gas that is evolved is actually passed through lime water and it turns lime water milky, the moment it does that, we suspect, or rather we infer, or we conclude that that particular gas is actually carbon dioxide. So we say that the colorless, odorless gas that is evolved, that turns lime water milky, is actually carbon dioxide. So you see that there is a process that we are using. So maybe you want to identify, you are using a chemistry expert system or whatever, okay, and you want to use it to guide you towards a qualitative analysis of a compound that you have in your chemistry lab, and then you say you tell the system, I have a compound like this, I want to understand the compound, or I want to understand the constituent of the compound, and say, so the expert system can also now tell you, okay, heat the compound, heat it at a certain temperature, and then you put it on fire, set it on fire, and then it tells you to observe what is the color of the gas, and you just tell the expert system, at this point in time, you are giving the expert system facts, okay? So that color is a fact. You see, the color of the gas is actually colorless, Or if you begin to suspend brownish color, now then you are talking about maybe there are ion compounds in that, or rather the compound that you are hitting is an ion compound or whatever. Okay, so that's the point. I'm not here to talk about chemistry. It's been long that I left chemistry. Okay. I want to believe that you are still following me. Okay, so that process that you follow certain processes before you arrive at a certain conclusion is actually what is known as forward chaining. And the inference engine can use this particular approach to arrive at a certain conclusion. Okay, that is it. Then the next one is backward chaining. Now, when you look at, I want you to pay very good attention to these two diagrams. You know, these two diagrams, they represent, or that, rather, they look alike. They looked alike. But one of the mistakes that students do make is that when I give this as an exam question, they forget the direction of the arrows. They forget the direction of the arrows. So when you talk about the forward chaining, the arrow proceeds from the left towards the right. But when you talk about the backward chaining, you notice that the arrow goes this way for backward chaining. Okay, that is backward chaining. And the forward chaining, in the forward chaining, you see that the arrow goes forward like this. Okay, so that's very important. So in case if I want to ask you a question, maybe to differentiate this with particular examples, I may be needing you to draw the diagram and then explain from the diagram. So the mark for the diagram will be removed if this particular, when we talk about forward, you know that one of the key things I'm looking for is the direction. Okay, when we talk about backward, I'm also looking for direction in the reverse direction. Okay, so this inference engine mechanism starts with goal and then works back to determine the necessary conditions or facts that support that goal. You say you will have malaria. What are the things that support malaria? So the system will begin to query you on that to check this conclusion that you are telling us about. Is it real? So it's possible that someone goes to a doctor for a consultation and then he goes there to tell the doctor, hey, doctor, I feel I have malaria. Or rather, doctor, I know I have malaria. You have already concluded. So maybe the doctor will begin to now ask you, do you have headache? Do you have fever? Do you have this? Do you have that? So the doctor is now beginning from the goal that you have presented to work back to the symptoms that actually causes malaria. So some expert systems can be built in this way, and then you can have an expert system that actually uses the two. So the expert system may begin to, maybe when you come to it and you start with your goal, then it will switch to the mechanism, the inference mechanism that uses backward chaining method. And then if you come with facts, you want to know what is happening to you, the expert system will use the forward chaining approach. Okay. So at the initialization, the system starts with a goal to be proved, okay, and then starts working back to start finding rules that conclude the goal. It goes further backward to find other conditions or sub-goals that needs to be satisfied for the rule to hold. Okay, the goal matching process is repeated until the conditions are met or disproven. So the expert system determines if the goal is achieved based on the satisfaction of the sub-goals. Right. Okay, now let's look at the application areas of expert system. You have medicine, you have expert system in medicine. And like I said, it's not only human medicine. We have in finance, for fraud detection, investment advice, and so on and so forth. In engineering, you have expert system that can be used for diagnosis, process control, and so on and so forth. And then in agriculture for disease detection, farming assistance, and so on. Okay, and I want to believe that some of you may, or rather may decide to do your projects, carry out your projects in any of these areas. It will just require you to follow the process for the expert system development. Okay, what then are the challenges of expert system? Number one, experts may not be conscious of all the knowledge there is in a domain. I think I've mentioned this before. Okay, and somebody is an expert does not mean that he knows all things. And so I say something about knowledge acquisition that you may want to use questionnaire to get information, rather to acquire knowledge from different experts, and then you aggregate those knowledge and then put it to your knowledge base. Hence, eliciting knowledge has to do with an aggregation of experts' knowledge, which is difficult. Okay, experts' inability to explain what they know in an understandable manner is also a challenge. Somebody may become an expert but is not able to impart that particular knowledge that he has in that domain. Okay, another thing is inadequate elicitation technique. Okay, inadequate elicitation technique from the knowledge engineer. You are not properly guided, you are not grounded in eliciting knowledge from the domain expert. So that will actually hamper that particular knowledge, or rather that particular expert system that you are developing. So the functionality of that expert system, how well that expert system performs, is actually directly proportional to this. It's actually directly proportional to what we are seeing. Sorry, got a message now. Okay, so sorry, I say that what am I saying? The functionality of an expert system is directly proportional to some of these things. Number one, the expert's ability to explain the knowledge he has. The expert's ability to have consciousness of at least greater percentage of knowledge in the domain experts. Number four, inadequate elicitation technique. If the knowledge engineer does not have what it takes to elicit proper information from the domain experts. Okay, and then we have evolvement of knowledge over time, which I talked about, that is necessary for maintenance and flexibility issues that has to do with the expert's knowledge. Then handling ambiguous and incomplete data. How do you handle it? That is a challenge. That is a challenge. What are the benefits of an expert system? It provides uniform solutions. It can be used anytime, even when the expert is there or when the expert is not there. It provides explanations for the decision it takes. Please note this. I want you to understand this. It provides uniform solution because it is drawing inference from the same knowledge base. Are we together? Now, it can be used anytime because it is deployed in a machine, and that machine may be your mobile phone or whatever. Okay. It provides explanation for the decisions that it took. So as to the purpose of these things is so as to actually inculcate trust in the lives of the people that are using the expert system. Then it saves costs. It saves costs. Imagine when you are consulting a doctor over your mobile phone, okay, and when you are going to the hospital. So it's not just cost; it saves time. Because when you go to a hospital, it's possible in our environment that you are going to waste the whole day there because you are following a protocol. Okay, then expert systems have advanced. What then are the recent advances that we can see in expert system? We talk about its integration with machine learning technology. So improved with that integration, we have improved performance and adaptability, which is made possible by the integration with machine learning. Then there is the integration with cloud computing technology. Cloud computing technology. Okay, it's increased accessibility and scalability made possible by the use of cloud-based expert systems infrastructure. Okay, these are the recent advances. And I want to believe maybe there's an integration of blockchain that may have also been included in expert systems development. Okay, thank you very much. I think this is the place that we are bringing this class to an end. So can I entertain some questions if you have questions? 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 Okay. In the absence of any question, please, I want us to call it a day. Do we understand?